Hi, welcome to the 12.3 lesson on dot products. Um, we're going to dive right in and look at a diagram that is one that's very common diagram to describe frequently occurring physical relationships in two dimensions. So this is drawn as a triangle, but notice that the dotted line here is just an aid. We're really interested in force F as the main idea in this picture. And if we drop the vertical line down to another vector, in this case it's drawn horizontally, to close up a triangle, even though we see the V vector is much longer than this side of the triangle, this piece right here we'll come to call the projection of vector F onto vector V. And this expression right here, the length, is the magnitude of F times the cosine of theta, cosine giving you the adjacent length. So this should be a very familiar calculation in basic right triangle trigonometry, couched in vector terms. Okay, so this will be a projection, and we'll dig into that a little bit more in a moment. So just want to introduce that diagram that you're going to see a whole lot with vectors. So this is the more general situation, simply two vectors drawn with the angle between them highlighted. We call it theta. We can measure it usually in degrees for practical problems, on occasion in radians, but it's not implied that it has to be one or the other. Just know that we use degrees much more frequently. Okay, so there's a formula for to calculate the angle between two vectors, and I'm going to kind of back into this, the derivation of this. I'm not going to make you sit through the whole long derivation, but I'm going to show it to you in the book. So this is a very involved looking formula. They write it as theta equals. You could also say the cosine of theta equals this big long expression right here. Now, we've got to come up with that. I can't just throw a formula at you and not tell you where it comes from. So checking my notes over here, make sure I'm following what I want to do. So I want to peek over here at the proof of this idea. So they drew our picture here, the angle between the vectors u and v, but they closed it up with the vector that represents the third side of the triangle here, so that we can apply the law of cosines. But they're using vector expressions. The length of vector w squared is the length of u squared, the length of v squared, minus 2 times u's length times v's length times the cosine of theta, which is the familiar law of cosines. And then they work this around. I want you to notice how they bring this term over, and then they solve for u squared, they have an expression for v squared, they have an expression for w squared, which they then substitute back into the main problem, strictly in terms of u1, u2, u3, v1, v2, v3. So it's a long, tedious recital of subscripts here, and they bring this down to this expression here on the left in terms of vectors, and over here in terms of vector components. And that's where we begin to see this u1 v1 plus u2 v2 plus u3 v3 expression for the first time. And since this expression is equal to 2uv cosine theta from the original law of cosines, we then take out the vector squared expressions, and we see the beginnings of what winds up in our final formula. The length of u, the length of v times cosine theta is that interesting collection of products here, solving for cosine theta and then expressing it as inverse cosine. We have a formula for the measure of the angle between two vectors. So without dragging you through every little subscript, that is the proof of this formula. So what we wind up with, you see this sum of vector components, products of vector components. We're going to call this expression the dot product of u and v. So it is related to the angle between the vectors u and the vectors u and v, rather, but it's not equal to like a practical quantity that you could draw. Notice how this is all scalars, multiplied and then added. So the dot product of two vector quantities is a scalar quantity, and that's the main feature of this little formula that I want you to pick up on, as well as how to use it to find the value, the scalar value of a dot product. Okay, so the dot product formula and how it's related to the angle between the vectors, very important formulas you will use again and again and again. Okay, so we need to practice taking dot products, recalling from the formula on the other page that this would be, you could do U or V in any order. This would be U1, U2, and U3, V1, V2, and V3. And again, you can pause this to go work out the problem for yourself if you like. And then our formula has U1, V1 plus U2, V2 plus, let's make that look like a U, U3, V3, and we just have to fill in the numbers. So 1 times -6 plus -2 times 2 plus -1 times -3. So that's going to be -6 minus 4 plus 3, -10 plus 3 is -7. So certainly a simple calculation. What is not simple is grasping the meaning of this product, because you cannot draw a picture of a straight up dot product. There is a relationship to the angle between the vectors, but this scalar number, -7, is not a physical quantity in the picture of these two vectors and the angle between them, merely a relationship there. So notice this quantity is the numerator of the inverse cosine expression in the theta formula. So in IJK form, no different. We're going to say 1/2 times 4 plus 3 times -1 plus 1 times 2. So 2 minus 3 plus 2 is 1. So dot products are easy to calculate algebraically. Okay, now if we want to take the expression in Theorem 1 that had the U1 V1 plus U2 V2 plus U3 V3 formula and replace that with the dot product, which is its equivalent, then we get a nice little formula that gives us theta strictly in terms of quantities we can calculate on the calculator. So the dot product of UV divided by the magnitude of U times the magnitude of V, and then we take the inverse cosine of that quantity and it gives us theta. So, you guessed it, we're going to try this. Find the angle between these two vectors. So, okay, so we're going to say theta equals the inverse cosine. Remember, we've got to do U dot V over the length of U times the length of V. And it's just straight up multiplication. You can put the dot here or not. But remember, magnitude is a scalar quantity, so this is just two numbers multiplied together here. So we need to get the numerator 1 times 6, -2 times 3, and -2 times 2. And on the bottom we need the magnitudes. So magnitude of U is going to be the square root of 1 squared plus -2 quantity squared plus -2 quantity squared. Square root of 9 is 3. And the magnitude of V is going to be the square root of 36 plus 9 plus 4. So 45, 49. The square root of 49 is going to be 7. So we're going to have 3 times 7 on the bottom here. And then we just need to clean it up. -4 over 21. And then we go to our calculator, and it did not specify rounding, so I would always give a couple decimal places when they don't. Since we have no context to judge how many decimal places is appropriate, I'd say go ahead and give me 2. I'm not going to count off for giving too many, but don't round to the nearest hundred or unit. Always give me a couple of decimal places. So the 100.98 degrees is the angle between these two vectors. Okay, again, algebraically, pretty simple calculation, and we need to practice and see how they're going to lay these problems out for us. Anytime it's find the angle, even if it doesn't use the word vectors in the problem, the reason why they came up with a way to do it with vectors is it's actually easier than law of cosines. You could whip out the law of cosines if you wanted to do the distance formula 3 times, or since they gave you a picture, how nice of them, you could do the Pythagorean theorem to get the 3 lengths and go to town with the law of cosines, but it is so much easier with vectors. Okay, watch this. AB, the side AB, right here. So we're going from 0, 0, and of course only in 2 dimensions. It would be the same in 3. If we treat AB as a vector and we do the head minus the tail rule, then the AB vector, 3 minus 0 and 5 minus 0. Well, it's just a position vector, so it's pretty easy to name the components. Then we do AC, and I'm choosing these two because their tails are at the origin, so they're easy position vectors. This is the vector 5, 2. And then if we want to find the angle between them, inverse cosine of AB dot AC. Oh, wait a minute. Look, I'm going for this angle, aren't I, in the way I set this up? Well, okay, that's nice, but I just realized it before I dive in too far that I would have been getting the wrong angle. So I'm going to stop right here, and I'm going to go get the vector BC and fix my mistake. So you got to watch out which angle you're solving for. We need the angle between BC and AC, angle C. So BC is going to be, let's see if I call this the tail, call this the head minus tail, 3 minus 5, and 5 minus 2. So we'll find the vector between, the angle between these two vectors, and that's going to be theta equals the inverse cosine of the dot products, so 5 times negative 2, and 2 times 3, and the magnitudes of AB and AC. So this is going to be 5 squared and 2 squared, square root of 29. And then this one is going to be the square root of negative 2 squared and 3 squared. All right, so that was a poorly drawn 13. So we have the square root of 29 times the square root of 13. So inverse cosine of negative 4 over, and something you can punch in your calculator from here, and you should get 79.03 degrees, rounded to 2 decimal places of accuracy. So if I hadn't gone to the extra trouble of finding a vector I didn't need and starting to calculate the wrong angle, this would be a pretty short problem compared to other ways that you've had to do it. Okay, so we need a definition right now of the word orthogonal, because you know what the definition of perpendicular is. And in geometry, you never had to deal with the perpendicularity of vectors. So if two vectors actually touch each other and cross and make a 90-degree angle between them, they're definitely perpendicular. We need to expand the idea of perpendicular vectors to include the idea of orthogonal. Orthogonal means that if they were placed so that they touched each other, the angle between them would be 90 degrees. So remember how vectors are not married to a single position in space. If they don't actually touch, but if they did, they would make a 90-degree angle, we're going to call them orthogonal. Actually, orthogonal is the bigger word. Two angles, or the angle between them, is 90 degrees. Orthogonal implies they don't have to touch. Perpendicular implies they are touching each other. So an actual set of vectors that cross one another, or that meet at in heads or tails, that make 90 degrees are perpendicular. If they are actually like this, where if this one was slid down, it would make 90 degrees between them, we would simply call them orthogonal. Okay. So here's the definition officially. Two vectors u and v are orthogonal if and only if. A great way to write if and only if in your notes is IAOI. You're going to see that phrase a lot in math classes. If you continue to take a lot of math classes in college, there's your note-taking shorthand. Very specifically, the rules of logic only allow this phrase, if and only if, in definitions. because definitions are statements that are true forwards and backwards. And if they're not true forwards and backwards, they're not real definitions. They're not good definitions. So look here. If the vectors are orthogonal, then their dot product is 0. And so it'd be true backwards. If the dot product of two vectors is 0, then they're orthogonal. That's the meaning of this, that you can write the statement forwards and backwards, and it's true both ways. It's the test of a good definition in mathematics. So why would this matter? Well, if we go with this idea, the cosine of theta is the dot product of two vectors divided by the magnitude of the two vectors multiplied, then we can see how if theta, the angle between the vectors, was 90, cosine of theta would be 0. So implying that the dot product is 0. So it's a very sound definition, very much related to the angle between the vectors. Okay, so let's see if we can decide if vectors are orthogonal or not. So we're given two vectors. Are they orthogonal? Well, if their dot product is 0, yes. So the dot product, there we go. 12 minus 12 is 0. So yes, these are orthogonal. Very simple test. Also works in 3 dimensions. Notice how the I component is missing, so we're going to say that's 0. Very easy to overlook and say that I is 2 and J is 4. So be careful there. All right, then we've got negative 2 times 2 and 1 times 4. So we've got 0 minus 4 plus 4. Definitely orthogonal. All right. So, of course, when we learn a new operation, and of course this operation can only be done between vectors, not between scalars and not between a vector and a scalar. Well, we've already defined scalar multiplication, and we've been doing scalar multiplication since we were small children. So a new operation, a dot product, requires a vector times a vector. So they state that here, u and v and w are any vectors, and c is a scalar quantity. So u times v equals v times u. Remember, that's our commutative property of multiplication. And then here we've got u dot v plus w. Well, the distributive property actually applies to vectors. So we would distribute and we would come up with two dot products and their sum. So this is the distributive property of multiplication of vectors, of the dot product of vectors. We have a zero product property, the zero vector. Now recall, I told you the zero vector has no length. And now we see the zero vector dotted with any vector, and its product, its dot product is 0. And what did we just learn about the dot product of two vectors being 0? It means they're orthogonal. So this statement says that all vectors are orthogonal to the 0 vector. Okay, so I'm going to put a bar over a 0, and you know I'm talking about the 0 vector. Every vector there is orthogonal to the 0 vector because of this property right here. Okay, so now we have scalar multiplication grouped together differently. Does not matter if we put the scalar with vector u and then dot it, or we put the scalar with vector v and then dot it. We can also dot the products and multiply it by the vector. So this would be an associative property of multiplication. And then down here, a vector dotted with itself is the square of its magnitude. This one's not too hard to figure out. In fact, there might be a homework problem asking you to prove this. If you want to stop and think about it now, I'm going to let you think about that one. If you want to ask me about it, drop me a line in an email and let me know. Or you could use GroupMe. That's good too. All right, so I'm going to talk about vector projection. This is a very similar diagram to the one we saw on the front page. And once again, we've got a vector u going off in a direction different than the horizontal line here. Vector v is on the horizontal. We've got a vertical or perpendicular line dropped to vector v. So we're not implying that QR is a vector. It could be, but we're not drawing it as one here. And they've emphasized this side of the triangle, PR, as a vector by drawing this really thick, hollow line with an arrow on the end of it. And we're very interested in PR here. So the vector projection of u onto v, notice the order, okay? u onto v, and they write the symbol this way, the vector projection of u onto vector v, or in the direction of v. So memorizing this is one thing. You tend to forget it if you don't have a reason behind it. So I want you to pay attention to the word projection. Like a projector is something that sends light through film and puts an image on a screen. So projection, so light, the idea is light. So let's say I have a flashlight and I'm shining it specifically, wait a minute, wrong direction. I'm shining the flashlight directly down perpendicular to my horizontal. This vector then is the shadow that PQ casts when light is shooting directly perpendicular to the surface which the shadow is lying on. So think of a flashlight shining perpendicularly to the vector that it's being projected onto, as if the vector V is the screen that the movie is playing on while light passes through film. Okay, so PR is going to be shorter than PQ because in this little triangle, PQ is the hypotenuse. But with this quantity, this scalar quantity is the length of this vector right here. Okay, so this is their symbol we're going to use, the projection of vector u in the direction of v. So they drew it this way this time. In a triangle, you're going to have an acute angle here, given that the right angle is always at the end of the perpendicular here. This angle must be acute. But let's look at it this way. The angle between u and v is obtuse. So how does this work in that case? Well, if we were to have our flashlight projecting light straight down again, then this is going to be the shadow, and that's going to be the projection of u onto v. It's not literally onto the length of v, but this is where using the phrase in the direction of v is useful. Although it is pointing a different direction than v, this is a length, so we're not concerned with a negative sign here. Okay. All right, so let's look at the way they couch these problems when they're dealing with physics problems. So if U represents a force, and in this picture the force is the strength it takes to pull this box using a string here. All right, if U represents a force, then the projection here, this pink thick arrow, the projection represents the effective force in the direction of V. So a lot of people get confused by the word effective force. If you're going to pull on this string, you're actually pulling up some and horizontally, or some. So vertically some and horizontally some, because you're pulling it at a diagonal. So some of your force is being wasted in the upward direction because the implication here is you're not pulling so hard that the box lifts off the ground. Now, if you were to lower your hand down here and pull this way, then all of the force would be pulling on the box to move it. But if your hand is way up here, then some of your strength is being wasted in the vertical direction. And the effective force is this projection vector, which is always less than the force length up here, so the magnitude of the force. It's going to be bigger than the projection every time. So what did I have in mind to share with you there? So let's look at it this way. So we've got our projection, and U is our force, and the magnitude of U times the cosine of theta. This is our theta right here, okay? And this right here is a scalar quantity. The length of U times the cosine of theta. We want to project it in the direction of V, or project it onto V. So we take a scalar quantity and we multiply it by V, but not straight up V. We have to do just the magnitude of V, or excuse me, just the direction of V. A vector divided by its own length is a unit vector. So this narrows it down to length 1, and this multiplied quantity makes it the proper length to be the length of the horizontal in the triangle. So this is a really complicated expression, but this quantity right here, okay, u dot v and the length of v, okay? See how this is the length of u up top, okay? So this right here would represent the cosine of theta. If we multiply the cosine of theta by the magnitude of u, then this cancels. So I'm going to take it away. So the length of u cancels, and now that represents this part of the expression. Now we bring this down. That's the direction of v times the magnitude of v. And we see how this is going to go. So we're going to do some simple algebra here. I'm going to keep the u dot v from here. I'm going to express down here. We've got the magnitude of v squared. That takes care of this quantity. That takes care of this quantity and this quantity. And then we're just multiplying by the vector v. So this is a scalar quantity. A dot product is a scalar. The magnitude of a vector squared is a scalar. And v is a vector. So this is the formula for the projection of the vector u in the direction of the vector v. So this gives its direction and part of its length, and this gives the multiplier that makes the length the proper length. So that's something you have to think through more than once. This is on page 721 in the paper edition of your textbook. By the way, if you did happen to find an electronic version, the page numbers might be different. So I've left the figure numbers in, okay? Usually they're the same, even from one edition to the next, and if not, they're usually close enough you can find it. Okay, so we'll continue with this idea of a projection, and let's look at these diagrams. So in a triangle here where we have an acute theta, there's one case where we have an obtuse theta. We'll look at that differently. We have this expression that gives us the length of the projection vector that stops right here, even as v keeps going. By the way, v could be shorter. You could project it onto v, but remember, we're just going in the direction of v, so it really doesn't matter how long v is. It's just the screen we're projecting the image onto. If we deal with the obtuse angle, that we're getting the length in the opposite direction of v, they have let you know that if you're dealing with a problem where direction matters, there would be a negative sign. This is a scalar quantity, though, so length can't technically be negative. So I have a little problem with them putting it in this formula, but if you're on a coordinate plane and you're trying to express the fact that the length goes in the opposite direction of v, then there's a place for you to acknowledge that it's going the opposite direction of v, although length isn't technically negative. If you have a theta that is greater than 90, then the cosine of theta will be a negative number. Negative times negative makes a positive length. But it looks really confusing to folks to see that negative there when it says length. Okay, so here's how they're stating it. If the length of the projection vector is a, the magnitude of u times the cosine of theta, if theta is greater than or equal to 0, and it is negative length of u cosine theta, if cosine theta is less than 0. So they're just stating it in sentence form there. Okay, so we want to find a vector quantity. It says find the vector projection of u onto v and the scalar component of u in the direction of v. The scalar component of u in the direction of v. That would be just the length of that vector. So let's do this. The projection of u onto v, we know, is going to be u dot v over the length of v squared times vector v. So this is a scalar quantity right here as we go to fill in all of this. And so we've got the dot product, 6 times 1, 3 times negative 2, and 2 times negative 2. Then the length of v, 1 squared, negative 2 squared, negative 2 squared, Square root of 9 is 3. 3 squared, okay, and times the vector v. They wrote it in IJK form, so I'm going to write it in IJK form in my work. So let's clean this up. 6 minus 6 is 0, so we've got negative 4/9 times I minus 2j minus 2k. So our vector, and we want to distribute this through, is negative 4/9 I plus 8/9 j plus 8/9 k. So this is the vector that results from projecting u in the direction of v. Okay, so the scalar component, okay, that's going to be the length of u times the cosine of theta. All right, and we didn't actually find theta in this process, but let's see what we've got. We've got u dotted with the unit vector in the direction of v, okay, and that's going to give us 6i plus 3j plus 2k. We're going to dot that, and we're going to do, we've got our vector here. The length of v was 3, so we take our original v divided by 3, and that gives us 1/3 I minus 2/3 j minus 2/3 k. Dot these together. 6 times 1/3 is 2. 3 times negative 2/3 is negative 2, and 2 times negative 2/3 is negative 4/3. So we're going to have negative 4/3 as the scalar component of u in the direction of v. Okay, so, excuse me, I didn't mark that as a vector. Just the scalar component of the projection we've got here is negative 4/3. Okay, we've got a little setup down here that I want to familiarize you with for certain kinds of questions. Notice how this says u is the projection. Okay, so u is the projection of u onto v plus u minus the projection onto v, and if we clean this up, we see that these cancel and u equals u. So this kind of seems like a ridiculous statement. But what they're doing here is they're saying, if you think about that, oh, that's a terrible triangle. If you think about that right triangle, we had u, and we projected it onto v. Okay, so we got this horizontal component right here. That's the projection vector right here. Then u minus the projection vector. If you recall subtracting vectors, you go from the end of the first one, u minus the projection, in the direction of the other vector. So u minus the projection is going to be this side of it, okay, the vertical side of it. And so we're going to have this as u minus the projection vector. So this is the right triangle. The hypotenuse is u, the horizontal is projection, and the vertical is u minus the projection. Those are the three sides that make up the little triangle. So if we add these two vectors together, we get u. Now, why do we care to write it in this complicated fashion? So their comment down here, so the equation here expresses u as a sum of orthogonal vectors. We've broken u down into its horizontal and vertical components. How far over do we have to go? How far up do we have to go? Adding vectors as we go to get u. So it seems like a silly question a lot, but you are taking a vector and breaking it down into the horizontal and vertical components, which we do for lots of things. And it's why right triangles are so meaningful in math classes. Okay, so our first application, I'm going to talk about work. So we've got an object, a rectangular object here, and the point P, and I think they've drawn it in the exact center of the shape for theoretical purposes. This object has been pulled here a distance of d so that the point where we end is at Q. And they did it by pulling on the object with a force at an angle of theta with the horizontal. And so we know that that scalar component is the magnitude of F times the cosine of theta, that horizontal component to the vector. And so that's a familiar idea from a previous problem. So it says the work done by this constant force during a displacement, that's why they call it d, that's the distance it's been moved, is going to be this scalar length times the magnitude of d, so how far it was moved. So if you look at this, this is the magnitude of F times the magnitude of d times the cosine of theta. Well, that's just another version of the dot product of F and d. So we can calculate the work done, and work is in joules, I believe, if I remember my physics properly. So force is pounds if you're in the British system, or newtons if you're in the metric system. D is distance and whatever units you want to give. So if you're staying in the British system, a unit of work is called a joule. Excuse me, it's called foot-pounds in the British system, which is just a horrible unit to deal with. In the metric system, they call it newtons. No, newtons are force. Newtons times distance, that's joules, the amount of work. So it depends on what system you're in. I've forgotten all my physics stuff, but since it's an application, I got to pull it back out and dust it off. Calculating the amount of work done in joules is the force vector dotted with the displacement vector. Okay. Now sometimes the displacement vector you kind of have to come up with. So we're going to look at this problem in example 7, and this will be our closing. We want, let's see, if the magnitude of F is 40 newtons and the displacement is 3 meters and the angle between those two vectors is 60 degrees, the work done by the force F and acting, moving from P to Q in the previous diagram is what? So they're asking for work. We know that's going to be the magnitude of F times the magnitude of D. All right. We've got to think about a dot product. Since we don't have vector components handed to us in the problem, we've got to think about the dot product. Excuse me, I should be calling these vectors. The magnitude of F times the magnitude of D times the cosine of theta. Now those numbers we have. So the magnitude of F is 40 newtons, the distance is 3 meters, and the cosine of 60 is going to be handed to us right here, 60 degrees, to plug right into this formula. So 120, oh, I should have put, yeah, I should have put 60 degrees here. So this is going to be 120 times 1/2 is the cosine of 60. So this is going to be 60 joules of work done in moving an object 3 meters using 40 newtons of force and pulling at a 60-degree angle on it. All right, straightforward application problem. That's the end of the section, and thank you for listening.